Next up, we have Erin Snyder from Northwestern University and Chicago Botanic Garden. And Erin's going to be talking about examining trait variation in wild collected and commercial seed sources to inform restoration methods for urban post-industrial sites. So Erin, go ahead and share your screen. Thanks.
Yeah, thank you for having me. Um, okay, this should work. Let's see. Um, oh, actually, um, sorry, 1 second. Okay, we're just gonna go with the first setting. I'm sorry. Okay. Thank you so much for having me today. As mentioned, my name is Erin, and I'm presenting on my thesis research. Can everyone see that okay?
Yeah, that looks great.
Okay. Yeah, sorry for the delay there. Thank you for tuning into my session. My name is Erin, and I'm a graduate student at the Chicago Botanic Garden and Northwestern University. And I'm really excited to share with you my thesis research, which examined trait variation in wild collected and commercial seed sources to inform restoration in urban post-industrial sites. And my goal for the next 20 minutes is to just get you thinking a little bit differently about these post-industrial spaces and what role they could play in biodiversity conservation. So I'd like to start our conversation today not in a restored prairie or in a seed bank, but in the blast furnace. Based on responses to the pre-session poll, thank you to those who responded. Slag may be an unfamiliar term for some folks. Slag is a byproduct of the steel manufacturing process. There are a few different types of it, but generally when when iron ore, coal, and either limestone or dolomite are smelted together, slag is that collection of metal oxides like calcium, magnesium, silicon, and aluminum that float to the surface. And slag is drawn off the furnace just before molten iron is poured out for shaping and modeling into things like steel beams. And dating back to the 1800s, slag has been recycled and upcycled for use as things like high performance concrete and road pavement, but much of it still goes to waste. Slag would often be transported by rail to sites where ladle cars would tip the molten lava-like material into a dump, as seen here, or in some cases, as was documented at Bethlehem Steel's plant on Lake Erie in the 1940s, right into waterways. Along the southern shore of Lake Michigan, where northeast Illinois meets northwest Indiana, is called the Calumet region. As this rendering of historical ecosystems shows, this area was once a mosaic of dune and wetland habitats with marshes and small lakes and rivers. This region has a long history of human land management and is the ancestral territory of the Peoria, Potawatomi, the Miami, Oceti-Sakowin, Kaskaskia, and Kickapoo nations who were forcibly removed from their lands. Because of this area's growing or proximity to the growing city of Chicago, railroad hubs south of the city, and the abundance of elements necessary for industrial processes like sand and water, this region became the epicenter of the US steel industry in the late 19th and early 20th centuries. In this region, slag was used to fill in wetlands and parts of Lake Michigan in order to create additional acres of solid land that industrial plants would then build on. In 1996, a USGS project categorized heavily impacted soils in the region. This orange layer is digitized from that map, and it indicates where slag was used as the fill deposit. So on the right are some images of what this slag looks like today, taken from two sites on the Chicago side of the Calumet, which are represented by yellow pins over here. You can see my cursor. And these sites are now natural areas managed by the Chicago Park District. Images on the top are from Marion R. Burns Park, and on the bottom are from Big Marsh Park, where my research is focused. Big Marsh Park is a 297-acre site that is actively being restored by the Chicago Park District. There's a beautiful nature center. They even have like a BMX park and mountain biking trails. Some portions of Big Marsh, like under the bike trails, are capped with clay or topsoil. In other areas of the park, the clay or the slag is uncapped, like in those photos you saw on the previous slide. According to research-based or research grade rather, iNaturalist records, there have been over 300 plant species observed in Big Marsh Park alone. Using a floristic quality assessment of the species list, we know that it's roughly 60-40 native to non-native species. But what can we do to bolster the native species that have shown up here? What would happen if we brought species that could thrive even more? And does all the slag need to be capped, or is it possible to foster biodiverse plant communities in the slag? Ecologists and land managers working at Big Marsh have been advocating that these sites have unrealized ecological potential. And I've welcomed alternative restoration approaches like a habitat analog method. A habitat analog approach looks for biotic and or abiotic similarities between environments to inform restoration decisions, even if the analogous habitat may not have occurred in that exact place. Related approaches like a degraded state analog take this idea a little bit further. So if a habitat has been so degraded or so destroyed that it is ecologically or financially infeasible to return it to its historical trajectory, maybe we could work with existing site conditions rather than spend time, money, and resources to repair them. This approach has been successful in cultivating alvar plant communities, including restricted and threatened species on abandoned quarry floors, as you can see here. Slag has high concentrations of calcium, magnesium, and heavy metals. And based on the high pH, thin-soiled, pavement-like environment it has created, ecologists working with slag have suggested alvar or dolomite prairie as potential habitat analogs. These are two extremely rare habitats where bedrock is at or near the soil surface. The exposed calcareous bedrock creates alkaline soil that's very thin and rocky, and this harsh environment supports unique plant life, with stretches of bare rock providing refuge for poor competitors and rare species. These habitats have been nearly lost to, ironically enough, industry. Alvars bordering the Great Lakes were quarried for limestone, and dolomite prairies quarried for dolomite rock. Limestone and dolomite are key ingredients in the steel smelting process. So there's this kind of sad but really interesting connection here that it's entirely possible that limestone are quarried on the Upper Peninsula of Michigan or dolomite quarried in northern Illinois made its way to the Calumet region and was transformed by human industry into slag. In summary, folks think that dolomite or alvar plants may do well here, but we need to try growing these species in slag first and see how they respond. Which brings us to the motivating questions for my research. I'm going to provide quick answers for 1 and 2, and then discuss question 3 more thoroughly, but always happy to chat offline about any of them. So does slag resemble dolomite prairie soil? In short, kind of. We found that uncapped slag had a similar pH and texture to dolomite prairie soil, but when we looked at soil available nutrients using plant root simulator probes, we did not see much overlap between uncapped slag and dolomite prairie sites. Interestingly, we found that nutrient supply rates of nitrogen and phosphorus were higher on uncapped slag than in clay or topsoil capped slag. This may be because it's less densely vegetated right now, but previous research has found that slag has similar organic matter content to other urban soils. So meaning slag may not be as nutrient poor as we might expect. However, it is important to note that this is only one dimension of soil ecology. Additional soil data from Big Marsh Park and remnant dolomite prairies are needed to make a more complete assessment. To test if slag can provide refuge for native species that grow in dolomite prairies, we first had to see if these species would emerge and establish on slag, or would emerge on slag. We didn't run a separate germination experiment, but we recorded emergence data for the seeds that we sowed in our primary experiment. And on average, emergence rates were lower on slag compared to topsoil, which aligns with previous research that ecological succession is slowed, but definitely not prevented on slag. Based on this finding, we would recommend a higher seeding rate when sowing on slag. But it is notable that for a few species in our study, emergence rates were equivalent across soil types. Because we had successful seedling emergence, we were able to dig deeper with question 3. So this was our central experiment. Because slag has not historically been considered for the restoration of dolomite prairie species, it's unclear where seeds for these efforts should be sourced. To address if wild collected seed could be better equipped for slag than commercially grown seed, we grew plants from both sources in slag and topsoil. And we measured several above and below ground traits that we know impact how plants survive in order to assess their performance. First, I'll talk through our experimental design, and then I'll share a few key results. So these are the 8 species that we used in our study, based on floristic inventories of Illinois dolomite prairies and advice from experts at the Chicago Botanic Garden. We selected 3 forb and 3 grass species. They are a mix of plants that can occur in multiple prairie types, including dolomite prairies, like Penstemon hirsutus and Schizocarium scoparium. But they also include some more range-limited dolomite endemics like Clinopodium arkansanum and Deschamps cespitosa. We also worked with federally threatened Tetranarius herbacea and federally endangered Dahlia foliosa, which are characteristic of dolomite prairies. I know this crowd is extremely familiar with seed sourcing best practices and is acutely aware that we often don't have enough seed to meet large-scale restoration needs. For these reasons, I wanted to test both wild collected and commercially sourced seeds and compare their performance in slag. So I identified accessions from the Chicago Botanic Garden seed bank from dolomite prairie habitats. In 2 instances, there were no accessions from dolomite prairies, so I selected accessions from a gravel hill prairie and a sand prairie, which offer some similarities. For example, gravel hill prairies are high in calcium and dolomite prairies are high in magnesium. And some previous analysis of Big Marsh Park slag has found that it tends to have a high sand content. So for the commercial source seed, I ordered from local nurseries. They were able to provide county level information about their seed. And I tried to source as close to Cook County, where Chicago is located, as possible. For each of these 6 species, 2 seed sources were sown in slag and topsoil that we collected from Big Marsh Park. So the slag came from an uncapped area and the topsoil came from a topsoil capped area. In total, there were 4 treatments per species. The related experiment with threatened and endangered species differed slightly in that we had only 1 seed source for each. So the Dahlia foliosa was sourced commercially, and the Tetranarius herbacea came from the Chicago Botanic Garden seed bank. And it was actually a 25-year-old accession that we were allowed to use because it didn't have any location information attached to it. So it can't be used in Illinois state restoration efforts. But really cool that we were able to get 25-year-old seed to germinate on slag. Spoiler, but seedlings were grown in a greenhouse environment, as seen here in images on the top of your screen. When they reached 8 to 10 weeks of age, we randomly selected individuals for harvest, and then we collected data on above and below ground traits that impact plant survival. To measure root traits, we washed root systems and floated them in water and then took scans, as you can see this image in the bottom center. And then we used an imaging software to process those scans and calculate the root trait measurements. In total, I used 9 traits in my analyses, and each of these traits was calculated per harvested seedling across the 4 treatments. And then working with all the seedling data from 1 species at a time, I tested whether traits varied by where they came from, so seed source, or what substrate they were grown in, so the soil type. While seedling responses were largely species specific, there were a few interesting results that I'd like to highlight today. In most cases, seed source alone did not explain trait variation. Both wild collected and commercial seed sources established and grew in slag. When seedling traits did show significant variation, it was more frequently explained by soil type than seed source. And there were some instances where seed source did matter, particularly for two of our forb species, but neither source consistently outperformed the other on slag. These results from early life history imply that both readily available commercial seed and wild collected seed would be suitable for seed-based restorations on slag. So meaning options are not limited, even though it is this kind of weird, funky environment. Folks can make seed sourcing decisions based on their own management goals, species availability, etc. Next, I'd like to share a bit about how species showed responses to treatments through trait variation. So the three grasses in our study responded primarily through root traits. Altogether, the grasses responded significantly to 5 out of 9 traits, and 4 of those 5 were below ground traits. Only one species showed significant variation in an above ground trait. Shoot, root, and total biomass did not vary significantly for any of the grasses. So if we had just looked at biomass or vegetative height values, which are commonly used indicators of plant performance, it would appear that the grasses did not vary much among the 4 treatments. The 3 forbs reacted a bit more variably, and responses were largely species specific. But the only consistent response for forbs was in a below ground trait. Seedlings have thicker roots in slag. Again, this was the only trait response that was common among all 3 forbs, with a slight caveat that for Penstemon hirsutus, this was true only for the commercial seedlings. But it's interesting, and the key takeaway here is that these common trends in trait responses would have gone unnoticed had we not measured root traits in our study. If we had looked at above ground measurements only, which many studies do, we would have missed instances of trait variation. Below ground traits have been definitely getting more attention in recent years, but they're still often underutilized in restoration ecology studies. And while traits of above and below ground plant organs can coordinate, research suggests that above ground patterns cannot be broadly applied to root systems. So we really do need to be measuring root traits, especially when substrate is as different and unique as slag. Hopefully that got you thinking about root traits. And next, I'd like to share results for the 2 threatened and endangered species in our study. Again, this sub-experiment with these species had only one seed source across the 2 soil types, and seedlings were harvested at 12 weeks of age. So for Tetronarius herbacea, we found that the only significant difference between soil types was in plant height. Seedlings grew taller in slag. And other than plant height, performance was equivalent between the soil types. Interestingly, we were able to hit our sample size for both the topsoil and the slag, but interestingly, we observed higher seedling mortality in the topsoil. We saw very little die-off in slag for this species. The Dahlia foliosa showed more variation between soil types. We observed significant differences in 4 out of 9 measured traits. In slag, seedlings were taller and had thicker roots. And in topsoil, seedlings invested a greater proportion of their biomass in root systems, but roots were thinner. If anyone is really interested in the plant trait stuff, I'd be more than happy to connect at some point today. But the key takeaway here is that threatened and endangered dolomite prairie species emerged and established in slag. And there are some cute little seedling photos of them growing in slag in the greenhouse. So based on these early life history results, these rare species could be used in seed-based restorations of slag, especially the Tetronarius herbacea, which performed as well on slag as it did on topsoil. Now I'd like to very briefly touch on bonus experiment that we did. It was field-based and we had a lot of extra seedlings from this threatened and endangered species case study. And since they're rare, we didn't want to waste them. So based on our greenhouse experiment, we knew that they could grow in slag. So we worked with the Chicago Park District to plant the extra seedlings at Big Marsh Park. In July, we potted up seedlings in the greenhouse. In October, we moved them outdoors to harden off. And in early November, we planted them in an uncapped slag area of Big Marsh Park, which you can see on the right here. November might seem late for transplanting, but this came at the recommendation of experts in Ohio who have been restoring Tetraneris herbacea populations um, in former quarry sites around Kelly's Island on Lake Erie for several years. And they mostly work with plugs, and they've had greatest success when planting out Lakeside DZ close to frost. So since we had more Tetraneris herbacea seedlings than Dahlia foliosa seedlings, we went with the late fall transplant date. The following spring, they started to emerge, which was really exciting. And based on our surveys, most seedlings survived the transplant and winter. But by June, nearly all of them had died, or at least appeared dead based on visible above ground vegetation. However, I don't think that this means that slag can't support these species. It was a pretty weird spring and early summer in the Chicago region. April 2023 was a record hot month. It reached 83 degrees on April 13th. So just as these species were starting to get started for the season. And this was followed by Chicago's driest May in 30 years. Then by June, we were in a severe drought, according to the US Drought Monitor. And slag is certainly a harsh environment, but our greenhouse experiment showed that these species can emerge and establish in it. And additionally, the soil available nutrient data that I collected showed that macronutrient supply in uncapped slag is in a range capable of supporting plant growth. So I do think that this abnormally hot and dry weather contributed to the near total mortality we observed. It's possible it just was not a good year to be a plug, but it would be interesting for future studies or land managers to try direct sowing these species in slag and see how they do. But these are perennials, and I'm hopeful that despite things looking dismal above ground, they persisted below ground and could reemerge this spring. Tetraneris herbacea also reproduces vegetatively via rhizomes, so I'm not counting these transplants out yet. I look forward to checking on them in a few months. So I'll leave you with that little cliffhanger. And there are many, just next time that you hear slag, I hope that you remember that slag is capable of supporting dolomite prairie plants, including threatened and endangered species in critical need of habitat, and that readily available commercial seed would be suitable for starting dolomite prairie plant communities on slag. So I hope that changes your perception of these post-industrial spaces a little bit, and challenges maybe when next time you're driving from Indiana to Chicago, what could be possible in these landscapes from a restoration perspective. There are many people to thank that helped make my thesis research possible. My thesis committee members, Doctors Becky Barak, Andrea Kramer, Kelly Kazak McInnes, and Lauren Umek. I'd also like to shout out my REU and College First interns who helped me deal with all of the seedlings from the greenhouse experiment that summer, Angelica Ostiguin and Esmeralda Juarez. There are lots of folks to thank from CVG. I know a lot of folks are watching up there, so hey guys. And there's a full list of citations and more information available on my website, which you can access by scanning this QR code. The link is there, and I'll also drop it in the chat or like in the Whova chat too. But that's all I have today. I'm happy to take questions.
Thank you, Erin, very much on that presentation. You do have quite a few questions. The first one is, was the growing medium for the slag test group in the containers mixed with anything else?
No, it was just slag that we filtered through, I believe, a size 4 sieve to filter out some of like the larger rocks. So as was visible in some of the photos, like there are some really large rocks that would have totally filled up a PT98 cell, and then there would have been no soil. So we filtered both the slag and the topsoil through a size 4 sieve. And then when I potted up the plants that we then put into Big Marsh, I put some of those rocks back into like a larger container with then the filtered slag. But no, just the slag and the topsoil.
Great, thank you. Can you give folks some more detail on how you floated the roots and what calculations you were looking for? And then secondary question is, what type of scanner or software did you use for this?
Yeah, so I followed kind of the protocol laid out by Larry York and others at the RiseVision team. So this RiseVision Explorer is an open source software, and they have dimensions for like how to like dimensions that they recommend for an acrylic box to create. And there are some great folks at the Botanic Garden who are working on root trait projects themselves, like Jacob Zeldin and Tessa as part of the BII project, and they had done some root scans. So they were a great resource for me on what size box to use. But we were using like an Epson 10,000 XL scanner or something. It's our herbarium scanner at the Botanic Garden. And I had a tray with like lanes so that I could do more seedlings at once, since I was working with pretty small samples. But yeah, you just fill it with water, and the roots after we wash them, we put them in like damp paper towels in the fridge, and we made sure to scan them within a week of harvesting. And you just take a black and white scan and then upload it into RiseVision. And RiseVision has a great resource guide. There's also like a training on YouTube. I can definitely share that link that Larry York did, but it's an open source software. You can just download it and use it. And the root traits that we calculated from it, I looked at total root length, mean root diameter, and using those, then we also like calculated root biomass. So after they were scanned, we then dried and weighed them. We also had a portion of samples that just went right from harvesting to the dryer. So not all of our samples were scanned, but a portion of each harvest was scanned. So then using biomass, we could get like root mass fraction. I think we also used a volume measurement to then kind of back into root tissue density. And then we also looked at specific root length, but I can also type these out in the Huga and drop the trait names if folks are interested, but highly recommend RiseVision Explorer.
Thank you very much for sharing.
Yeah.
Do you know if anyone has looked at the mycorrhizal component associated with the plants growing on slag?
I don't know. I don't think anyone has here yet. I'm actually at like a research summit at Big Marsh right now. And someone asked this question of someone who presented on slag earlier. They were like, what about the microbiome and the fungi? And it seems like no one has yet, but I think it would be really interesting, and it's something I call out in my thesis, that this would be an interesting research area to go in, because there's some studies that show that like certain mycorrhizal fungi might shield plants from the effects of heavy metals, which like, I don't know. I don't want to speculate too much, but because it doesn't seem like the heavy metals are impacting germination the way you might expect them to if you were to test that in like a lab environment. But I don't know if anyone has yet. But if anyone does know and wants to share those papers with me, that would be great. But I know that a lot of the like novel ecosystem habitat analog research comes out of like folks working on mine restoration in Australia and Canada and like quarries and stuff. So they might have like.
Great, thank you.
Yeah.
I'll ask one more question. Is there a planned experiment to seed directly into the slag? Some species don't thrive as transplants and may do better when direct seeded.
Folks at the Park District have direct sowed some stuff. One of my committee members, Lauren Umek, is an ecologist at the Park District and works at Big Marsh. So they've direct seeded some things, and things have come up. But I know that there's a long-term transect monitoring project, but that's of stuff that has shown up here on its own, not stuff that has been seeded. So folks are definitely doing that, but we haven't tried direct sowing these threatened and endangered species yet. But Lauren has tried kind of like a generic prairie mix, mostly on the topsoil cap slag. But definitely lots of opportunities to explore what's going on the uncapped slag and try direct sowing there.
Well, thank you very much. Again, Erin, that's all the time for questions we have. I'll take the rest of them and post them into the Huva Q&A, and I'll pass it to Morgan.
All right, thank you so much.
Yeah, thank you, Erin. That was a really cool presentation and really fun research, I think, and cool direction.
Thank you. Yeah, thank you guys for hosting. Bye.
Yeah, thank you.